Any questions? So today I hope to finish correlated solution concept. It took much longer than I hoped for. But after everything we did, I think you will all agree that the simplest form of expressing a correlated solution or a correlated equilibrium was of the following form. So we can take it as a probability distribution, probability measure, I should say, over the set of strategy profiles, okay? So a probability measure over the set of strategy profiles is a correlated solution for the game gamma if and only if. So the easy way to think about this was, so a random device selects a strategy profile that selects a strategy profile and informs each agent about the component of S that corresponds to them. And with that information, we interpret it as that the player is recommended to play that. So the random device selects a strategy profile S that will be selected with pi of S. So the way we interpret that is player I is, so once S is selected, player I is recommended to play SI, okay? So given that he's recommended to play SI, using this, well, we had conditional probability here, but we simplified things. So in a way, we were asking his expected payoff from following the recommendation, okay, which we expressed it in the following form. Okay, was greater or equal to his expected payoff from playing something else. So these are small yield Bernoulli payoffs. So we had this for every I in N, for every SI prime in SI. If this condition holds, we call this probability measure over the strategy profiles a correlated solution or a correlated equilibrium of the game gamma. Okay? So far? Oh, I forgot to write that. Yes, yeah. Because I had something else in my mind. Thank you. Okay. Okay, so far, so good? So that was the simplest form. Actually, we started by using conditional probability, which is more intuitive, but that's what that simplifies things, okay? So let's do an example. Okay. So let's, again, go back to the battle of sexes. Game, soccer, opera, 2, 1, 0, 0, 2. Okay. So I don't want to write P, so I don't, to simplify notation, let's take pi of SS to be A, pi of SO to be B, pi of OS to be C, pi of OO to be equal to D. So actually, let me write those in here. So the probability that SS will be selected by this random device is A. The probability that SO is going to be selected is B. OS with C. O with D. Of course, A plus B plus C plus D is equal to 1. Okay. So, what conditions A, B, C, and D should, what conditions should A, B, C, and D satisfy for it to be a correlated solution of the battle of sexes game? Sorry? First of all, because it's a probability measure on S, so the first condition we have is A plus B plus C plus D is equal to 1. That definitely, irrespective of anything else, that should hold. So let's give everybody. So write the conditions. Okay. So actually what you have to do is write this. Okay. Let's give everybody a couple of minutes. So try writing it. Come on. What should we have? What is the condition that we should have? Conditions on A, B, C, and D. Come on, come on. Think. That's, I'm not saying. Think. So, need scrap paper? Paper? Come on. Again, the easy way to think about this is, what would happen if player 1 was recommended to play S? What would happen if player 1 was recommended to play O? Okay. Player 2 was recommended to play S. Player 2 was recommended to play O. So actually, you don't really have to memorize this formula if you get the idea. Anybody would like to share there? So actually, you're using the initial formula, well, the intermediate formula we gave, which uses conditional probabilities. So intuitively, it's more clear, but it requires more work. Anybody else? Anybody else? So, let me start. So we ask, if he is signaled S, so SI is equal to S, okay? What is, again, I'm going to put it in quotations, what is his expected payoff if he follows the recommendation? The quotation, it's not exactly expected payoff. For it to be expected payoff, I should use conditional probabilities here. But we saw that it's just a multiple of the conditional probabilities. So that's what we're going to do. So with probability A, actually with probability A divided by A plus B, his payoff is going to earn 2 liras. And with probability B over A plus B, he's going to get 0. But again, like we did before, we multiply it with A plus B, cancel with the condition probability. So writing this equation for S gives us 2A plus 0B. Now, if he deviates, well, there's only one thing he can deviate, play O. So if he plays O, when it's signaled S, his payoff is going to be 0 times A, right? Conditional probability A over A plus B. If we use this formula, it's going to be A. So the probability that you have here and you have here are the same. That's actually the place that we were most confused last lecture, right?
Can you shortly explain again why we have come to the probability measure from C over A plus B?
So actually, let me write it with conditional probabilities, okay? So if he's told to play S, what is the probability that his opponent is told to play S, given that he's told to play S? Okay, so if he's told to play S, he knows that his opponent is either told to play S or O, so he knows that he's in one of these cells. Okay, so using conditional probability, this would be A divided by A plus B. Okay, and so with this probability, given that he's told to play S, with this probability, his payoff is going to be 0, is going to be 2, plus with this probability, his payoff is going to be 0. So that's just Bayesian updating of his belief about with what probability will he be in this cell, with what probability will he be here in this cell. Okay? So if he deviates and plays O, nothing changes about the probabilities. With this probability, his payoff is going to be 0. And with the same probability, B over A plus B, his payoff is going to be 1. So his expected payoff, if he plays S, follow the recommendation is going to be this. His expected payoff, if he plays O, rather than following the recommendation plays O, this is his expected payoff. So for what we want is following the recommendation should not be worse than deviating from the recommendation. Okay? Now, if we multiply both sides of this with A plus B, okay, these will cancel. A plus B is positive. Nothing will change. Okay? Okay? So rather than using conditional probabilities, that's how we came up with this formula. Okay? Okay? So let me summarize that here. So we have 2A should be greater or equal to B. That's condition 1. Okay? That comes from he's told to play S. So let me erase this. What if he's told to play O? So let me write it again. 2 times A plus 0 times B should be greater or equal to 0 times A plus 1 times B. So is it? That's B. That's D. Okay. That's C. Yep. So we use the same probabilities. The probabilities doesn't change with the behavior of the agents. Okay? Like that. So condition 1, 2A should be bigger or equal to B. If he's told to play C, if he follows the recommendation, his payoff is going to be 0 times C plus 1 times D. That is D. That should be greater or equal to his expected payoff when he deviates, 2 times A plus 0 times B, so 2A. Again, these are not expected payoffs, but a multiple of the expected payoff. Okay? And then we do the same thing for player 2. If he's recommended to play A, it means that one of these outcomes, SS or OS, resulted from the random experiment. Okay? The random device gave us SS or OS. So with probability A divided by A plus C, his payoff is going to be 1. With probability C divided by A plus C, his payoff is going to be 0. That's his expected payoff if he follows the recommendation. 0 times A, again, probabilities doesn't change. 2 times C will be the expected payoff if he deviates. So that's A greater or equal to 2C. And then we complete this with if he's told to play O, his payoff is going to be 2D. If he follows the recommendation, it's going to be greater or equal to 1 times B if he deviates. Okay? So far? Did I make a mistake again? This one? Where did I get the A there? Yeah, that's definitely 2C, yeah. It should be these two numbers. Thank you. So AC, BD, yeah. Okay, thank you. Any questions? Any questions? So, these 4 conditions together with A plus B plus C plus D equals to 1. Any 4 tuple, A, B, C, D, which satisfies these 4 conditions is a correlated solution of this game. Okay? Any questions? Yes, sir.
Why only 4 tuple?
Sorry?
Only 4 tuple?
Well, because it's a probability measure on S, which has 4 elements. So we have to tell with what probability SS is selected, with what probability SO is selected, OS. So a probability measure on S can be represented with a 4 tuple, A, B, C, D. Okay? So A tells us with what probability SS is selected, B tells us with what probability SO, C tells us with what probability OS, and D tells us with what probability OO is selected. Okay? So a correlated Nash solution of the battle of sexes game is a 4 tuple. That is a probability measure on S, which satisfies these 5 conditions. Okay? Any questions? So all you have to do is solve them. Okay? So the nice thing about this is, like finding Nash equilibrium, Nash solution when there is mixed Nash, well, Nash solution of the mixed extension game, when there are 2 agents, it's a system of linear inequalities and equalities. Well, let me say a system of linear inequalities. Okay? So when there are 2 agents, finding Nash solutions of the mixed extension of a game and finding the correlated solutions of a game is solving a system of linear inequalities. But when there are, irrespective of how many strategies the agents have, but when there are more than 2 agents, finding correlated solutions is still a system of linear inequalities. Finding Nash solutions of the mixed extension is no longer linear. Okay? For the 2-agent case, it is linear. But when you have more than 2 agents, the equations you get is nonlinear. So actually, finding correlated solutions is easier than finding Nash solutions of a mixed extension game when there are more than 2 agents. Okay? Solving a system of linear equations. Okay? So actually, let's try to find at least one. Okay? So we're going to try to solve that. What can we do? Let me, okay. So that's what we have. So, any suggestions? Yep.
Let's say B and C
So you want to start with B and C? Equal to 0. So that's one thing you can do. Try giving values to some of the, so there are 4 variables. Okay? Try giving values to some of the variables and see what it tells about the other variables. Other things you can do is try to do a little simplification. So actually, before following what you said, let me go just try a few things. Okay? So because there's a point that I would like to illustrate. So let me give these numbers. 1, 2, 3, 4, 5. So let's see. for example, 1 and 4, let me write them better. So that's equation 1, equation 2, equation 3, equation. Okay. So for example, using 1 and 4, we can conclude that 2a plus d is greater or equal to 2b, right? So we can conclude that a plus, so 1 and 4 implies that 1 and 4 implies that 2a plus d greater or equal to 2b, which a plus b is greater or equal to a plus d is greater or equal to b. Okay? So that's what we know is whatever numbers that we assign to this cell, okay, it should be less than the sum of a and d. Okay? Okay? The reason that I'm doing this, sometimes what people do is they start with these, okay? So that implies that, and then maybe use more simplifications. Okay, for example, we can also conclude from here using 2 and 3 implies 2 and 3, a plus d greater or equal to c. Okay, so and then people keep using these and then find some values, a equal to something, b equal to something, c equal to something, d equal to something. Now, what you have to be careful about is the direction of the implications. Okay, these two imply this, and then if we conclude that at the end, for example, we got that this implied that a is equal to, I'm making up the numbers, 0.4. Okay, be careful about the implications. So these implied that a is equal to 0.4 or greater or equal to 0.4. But the implication, what we need is the other direction. It doesn't imply that 0.4 satisfies these conditions. So you have to be careful. Okay? When you're writing your implications, okay, make sure. So 1 and 4 implies this, but this does not imply these two properties, these two inequalities. Okay? So here, so what this says is that if this system has a solution, then it should be like this. But it doesn't say that this is something which solves the system of equations. Okay? That's a very common mistake when people work, well, most of the students, when they work, they treat all these implications like if and only if. And then they say that's the answer. No. It says if there is anything which satisfies this, it should be such that what you have to do is take these, plug it in here, and make sure that they satisfy. Okay? So that I wanted to emphasize, be careful about the logical arguments, the direction of the implications. Okay? And whenever you have two-sided implications, if and only ifs, write them. So this is true if and only if this is true, but the truth of this does not imply the truth of 1 and 4. Okay? So let's go to your friend's suggestion. So what was your suggestion? So your friend said, let's take b equal to 0 and c equal to 0. Okay? So if b is and c is equal to 0, these have no bite. Anything satisfies those. So b equal to 0. So everything here is free. So we can choose a to be anything, d to be anything, as long as they add up to 1. So, for example, 1, 0, 0, 0 is a correlated solution. Okay? And so is 0, 0, 0, 1, a correlated solution of this game. It satisfies all the conditions. So is 1 over 2, 0, 0, 1 over 2. It satisfies all these conditions. Okay? Again, this is not the condition I'm checking. These are the conditions that I'm checking. Okay? So, for example, alpha 0, 0, 1 minus alpha, where alpha is any number between 0 and 1, is also a correlated solution of the battle of sexes game. Okay? Any questions? Any questions? Any questions? By the way, what happens at this correlated solution? They play the Nash equilibrium S, right? What happens at this Nash equilibrium? They play the Nash equilibrium O, O. Okay? So far, so good? Any questions? Actually, one of your friends, I think it was you, right, made a remark about Nash solutions of mixed extension and correlated solutions. Do you remember what the remark was? It was? Well, not exactly, again, subset in quotation, because they're two different animals, right? So for example, what was the Nash solutions of this game? The mixed extension of this game? So let me write it here. The Nash solutions of the mixed extension game. This time I'm going to write it in the long way. It was 1, 0. Player 1 plays S for sure. Player 2 plays S for sure. So that's one strategy profile. That's one mixed strategy profile. The other one was player 1 plays O for sure. Player 2 plays O for sure. That's another. Okay. And then we had one more, which was player 1 plays S with probability 2 over 3, O with probability 1 over 3, and player 2 plays S with probability 1 over 3, and O with probability 2 over 3. Okay? So far, so good? So this animal is different than this. This is a pair of two independent probability measures, stochastically independent probability measures. This is one probability measure, okay? But again, we know that from these probability measures, we can construct a probability measure on S, okay? How do we do that? Let me erase that. Define mu hat in. So any list of probability measures where each component, so ith component, is a probability measure on the strategy set of player I, induces a probability measure on the strategy profiles, which is defined as, so for any S in capital S, mu hat of S, you can define it as exactly. Oops. Right? Just multiply them out, get the probability measure. Okay. So the claim what we had was, it was an observation made at that moment. I forgot who made it, but one of you did make it. So for any mu I, Nash solution of the game gamma, okay, so well, let me see. If this profile of mixed strategies is a Nash solution of the mixed extension of the game gamma, then mu hat is defined as above is a correlated of the game gamma. Okay? So this is the sense that any Nash solution of the mixed extension induces a correlated solution of the game. Okay? That was, again, in quotations, in a sense, the Nash solutions of the mixed extension is a subset, not in the mathematical sense, but it can be embedded in it, embedded into the set of correlated solutions. Any questions? Any questions? Any questions? By the way, as a result of this, we get something for free. What is it, what we get?
Nash solutions of regular game. Fierce to game are also.
Well, so again, it induces a correlated solution, but even something more important than that. It always. So we know that every finite game, the mixed extension of every finite game has a Nash solution. Together with this implies that every finite game has a correlated solution. Okay? So existence is guaranteed. Okay? So using this fact together with the fact that every mixed extension of a finite game has a Nash solution, we conclude that every finite game has a correlated solution. That's a corollary of this and the existence theorem for the Nash solutions. Okay? I'm not going to write it. It's a simplified. Okay? Any questions? Any questions? So let's go back to what we had. So for example, this, I'm going to call it mixed strategy Nash solution, induces this correlated solution. This mixed strategy Nash solution induces this correlated solution. Okay. What about this? So let's write that. So it will be both yes and no. It's 2 over 3 times 1 over 3. Okay. So the probability that, so we're looking at, this is the component which corresponds to the strategy profile SS. Player 1 will play the probability, the strategy S with probability 2 over 3. Player 2 will play the strategy profile S with probability 1 over 3. So as your friend said, it's 2 over 9, but this is a bit more informative. So the second component, we took it as the probability at which SO will be played. So that's going to be 2 over 3 times 2 over 3. Player 1 will play S with probability 2 over 3. Player 2 will play O with probability 2 over 3. And then 1 over 3 times 1 over 3. 1 over 3 times 2 over 3. Okay? So this is also a correlated solution of the Battle of Sexes game. Okay? Any questions? If you check, it will satisfy all the 5 conditions we have here. Okay? But we don't have to check it. We have a proposition which guarantees it. Okay? Any questions? Any questions? Any questions? So, how many correlated solutions did we find so far? Infinitely many, right? So, what else? Are there more? Is that it? Let me write the definition of a correlated solution again. I'll write it in 2 stages this time. Okay. Did I make a mistake somewhere again? I hope not. Okay. So, one more thing. So, pi is a probability measure over strategy profile. So, this is what we called S. This time I wrote it a little bit more explicitly. Okay. Yeah. Okay. Pi is a probability measure on S. So we can think of it as a subset of R cardinality S. Okay? So in this case, R4. Okay? So I can think of these like vectors in the cardinality of S-dimensional Euclidean space. Okay? So far, so good? So far, so good? Okay, so when working with Euclidean spaces, what kind of things can you do? If I can think of this as a vector, what can I do with it? I can take linear combinations, right? So take 2 probability measures, pi and pi prime. You can add them. Actually, you can multiply them with 2 coefficients and add them. After all, these are vectors. But there's a problem. Pi is a probability measure. Pi prime is a probability measure. You take the linear combination. The linear combination need not be a probability measure, right? Right? Okay. So, for example, if you let alpha 1 equal to 1, alpha 2 equal to 1, when you add pi and pi prime, call this pi double prime, summation pi double prime S would be equal to 2, not 1. So if the coefficients, first of all, are non-negative and sum up to 1, then the result would be also a probability measure. Actually, we have a special name for that. We call it the convex combination. So convex combination of 2 probability measures also gives you a probability measure, right? Okay. Well, a correlated solution is a vector, a probability measure. We know that there can be more than one. If I take 2 correlated solutions and take the convex combination, what would happen? Again, you would have, so pi is a correlated solution. You have this condition. Pi prime is a correlated solution. You have this condition. Okay. Well, multiply, actually, let me not be that lazy and write that down. Multiply both sides of this inequality with alpha, both sides of this inequality with 1 minus alpha. Because alpha is non-negative, the direction of the inequality will not change. Because 1 minus alpha is non-negative, the direction of the inequality will not change. Okay? And then when you add those two inequalities, what do you get? Summation, I'm just going to write it fast. You'll get this, which implies alpha pi plus 1 minus alpha pi prime, where alpha is a number between 0 and 1, is also a correlated solution of the game gamma. Okay? So far, so good? Which implies the set of correlated solutions is a convex set. Okay? So let's write that proposition too. Okay? So far, so good? Which implies that if a game has more than one correlated solution, it will have infinitely many. Okay? Any questions? By the way, we would not be able to say this with the initial definition of correlated solutions. In the initial definition, we had the random device. So how do you take the convex combination of random devices? But with this definition, which was less intuitive, but mathematically simplified, we're able to say things like that. Anything else that we can say? So this was an algebraic property. Can we say anything about topological properties of the correlated solutions? Sorry? Well, we didn't, it's closed. Is it always the case? Okay. So how do you check whether a set in Rn is closed? Well, there are several ways, but one of them is what your friend suggested. Take a sequence of correlated solutions, such that the sequence pi n converges to some probability measure pi. Okay? So pi is a probability measure, but we do not know if it's a correlated solution. It will be a correlated solution if it satisfies this condition, right? So for each n, pi n is a correlated solution. So for each natural number n, this condition holds. Actually, let me use k because usually we use n to denote the number of agents. Sorry about that. Okay. So if I take the limit of this as k goes to infinity, what happens? This will converge to pi because summation, this is a linear function of pi s. Okay? So that converges to pi, that converges to pi, and inequality will be preserved. Okay? Which would mean that if pi k, the sequence pi k converges to pi, pi will also be a correlated solution, which means that the set of correlated solutions is a closed set. It contains its boundary. So it's convex and closed subset of that set. Actually, we can even say more. It's bounded, so it's a compact subset. Okay? So algebraic topological properties of the correlated solution. Any questions? Yep.
Can you repeat how you understood the closed?
Let's take a break. After the break, we'll talk. Okay? I forgot to give that attendance sheet again. Okay, don't forget to turn in your homeworks.